In this video, we're going to look at the case where our steric number is 4, in which case we're going to end up with a tetrahedral electronic geometry in all cases. However, as we'll see, this tetrahedral electronic geometry will not result in a tetrahedral molecular structure in all cases. We're going to start with methane, the Lewis structure of which is this. And if we were to look at the steric number for this, we're going to take the number of atoms attached plus the number of lone pair electrons around our central carbon. Of course, there's 4 atoms attached to the central carbon. There's no lone pair electrons, and so our steric number is 4. That's going to give us, of course, the tetrahedral electronic geometry. It's going to end up with a structure that looks like this. It's 3-dimensional. We have to think of this molecule in 3 dimensions. This is a tetrahedral arrangement of the hydrogen atoms around the central carbon atom. And this hydrogen-carbon-hydrogen bond angle is the tetrahedral angle, which is 109.5 degrees. This is fairly straightforward. In this case, the geometry of the molecule that results is the same as the electronic geometry, the way the electron pairs orient themselves around the central atom. Other possibilities exist. Let's consider ammonia. For ammonia, the Lewis structure looks like this. And if we were to determine the steric number for ammonia, we're going to take the number of atoms attached, which is 3. We're going to add in the number of lone pairs, which is 1, giving us a steric number of 4. In this case, the resulting molecule and lone pairs look something like this. In this case, the black sphere is going to represent the nitrogen atom. The white spheres are going to represent the hydrogen atoms. And this foam loop is going to represent the lone pair of electrons on top of the hydrogen atom. And we see once again with a steric number of 4 that the electron pairs orient themselves in roughly a tetrahedral arrangement around the central carbon atom. Now we're going to need to remember this idea that these lone pair electrons that are more free to move are going to exert some pressure, some more electronic repulsion pressure on the bond pairs than the bond pairs exert on each other, and that's going to push these bond pair electrons to be a little tighter. That bond angle is going to be a little tighter than 109.5. It's actually going to turn out to be 107. This hydrogen-nitrogen-hydrogen bond in ammonia is 107 degrees rather than the tetrahedral angle of 109.5. When we describe the molecular geometry of ammonia, we don't call this tetrahedral because we ignore this lone pair of electrons. We just want to describe the orientation of the atoms when we're describing molecular structure. So when I go to describe the molecular structure, I'm just going to go ahead and remove this lone pair of electrons and sort of look at what the molecule looks like. And what we see here is there are 3 hydrogen atoms that all rest nice and easy here in the plane of the paper, but the nitrogen atom, it sits up above the plane of the paper. It's like a little pyramid with a triangular base. So I can draw a triangle here, and then the nitrogen sits up at the apex of the pyramid. And so this molecular geometry we call trigonal pyramidal. Trigonal because the base of the pyramid is triangular, and pyramidal because the entire molecule itself appears to take on a pyramid-type shape. Once again, the bond angles here are 107 degrees, a little less than the tetrahedral angle because the existence of the lone pair on the top of the nitrogen squeezes these bond angles in a little bit tighter than the 109.5 degree tetrahedral angle. Finally, we can look at the case for water. The Lewis structure for water looks like this. If we were going to describe the steric number for our central oxygen, we'll note that there are 2 atoms attached, and there are also 2 lone pairs, giving water a steric number of 4. So in the case of water, we have something that's going to end up looking like this, where we have 2 atoms attached and 2 lone pairs. The atoms, of course, are represented by these white spheres, and the lone pairs are going to be represented by these pieces of foam. So we see that the electrons orient themselves electronically, once again, in this tetrahedral arrangement. It's not a perfect tetrahedron, once again, because these lone pairs are going to exert a little bit more electronic repulsion on the bond pairs, and that's going to squeeze this angle to less than 109.5 degrees. Actually, in water, the hydrogen-oxygen-hydrogen bond angle ends up being 104.5 degrees. So because there's 2 lone pairs exerting electronic pressure on the bond pairs, we get even more distortion of the bond angle, down from 109.5 as the tetrahedral angle, 107 in nitrogen, and all the way down to 105 in water. So while we have this tetrahedral electronic arrangement, when we describe the shape of the molecule, once again we're going to ignore the lone pairs, because when we're describing the molecule, we just want to describe the shape of the locations of the atoms, and it's pretty easy to see if we just describe the shape of this molecule, we would call it bent.